So now let's look at this optimization problem, which is a little bit different. So we have a piece of wire that is 24 inches long, and it's used to form a square with the sides labeled X and or a rectangle whose length is 3 times its width, labeled Y. Determine both the maximum and minimum combined areas using calculus. Okay, so we haven't had to do that before. We're actually have to find both the max and the min using calculus. Show all work, give exact answers, etc. Okay, so let's start with the diagram up here. So we need the diagram and the variables. All right, well, we can make a square, right? And or we can make a rectangle. I'm not sure that I'm doing a very good job with drawing these, but bear with me here. Okay, now it said that the square has to have sides labeled X. So right here, it's telling you right there. So we want the sides of the square labeled X. Pretend this is a square. I did not do a good job of drawing that one. And then we have over here a rectangle whose length is 3 times its width. So the width is Y, and then the length is 3Y. All right. So we have our diagrams, and we have our labels and our variables. Wonderful. All right, so now step 2, we need an objective function. We need to look for something that we are trying to maximize or minimize. All right, well, let's see here. Determine both the maximum and minimum combined area. So I want the area of these two items combined. Okay, so the area on a square is x squared, and the area on the rectangle is length times width. So that's 3y times y, which is 3y squared. So the combined area is a function of x and y. It's x squared plus 3y squared. This is the square, this is the rectangle. All right, now we were given a constraint. At the very, very beginning of the problem, it tells us that we only have 24 inches of wire in order to build this. Right here, 24 inches of wire. So that's our constraint right there. Now the wire is used to build the actual square, and the wire is used to build the rectangle. Now keep in mind, you could build just one shape or both shapes, right? Okay, so what does that wire get us? The wire gets us the perimeter. So the wire is the perimeter, which is 24 inches long, right? Because perimeter is a single variable, like inches, as being a single unit. Because wire, perimeter, it's the distance around. That's one dimension. Right? You just bend it, but it's technically one dimension, as opposed to area, which is how many squares would fit in this, which is 2-dimensional. Okay, so perimeter. Well, let's see. The perimeter on the square, x plus x plus x plus x. So that's 4x for the square. The rectangle is y plus 3y plus another y plus 3y, which would be 8y. So that's the square. That's the rectangle, if you will. And together, they can only make 24, right? So you have to fit everything for the two items out of this 24 inches of wire. So obviously there's not going to be huge squares or rectangles. Now I have to solve this for one of my variables because I need to make one of my variables over here disappear. And it kind of doesn't matter which one you get rid of. I'm just going to get rid of the x because I think it'll be easier. So if I say 4x equals 24, take away 8y, divide both sides by 4, that's 4 equals 24 over 4 is 6, take away 8 over 4 is 2. And that's actually why I solve for x. Because if you solve for y, you'll be fine, but the problem is you'll end up with subtracting 4x dividing by 8, and that'll give you a fraction, and students tend to, not do as well with fractions, so I switched it. Okay, so step 4, I'm going to use the constraint to eliminate a variable, right, to get one variable. I have 2 to begin with. It's an area function of x and y, the square and the rectangle. So now I'm going to make it, because the square and the rectangle are related to each other, I'm going to make it a of y alone. So instead of x squared, I'm going to put in 6 take away 2y squared plus 3y squared. Done with step 4. Easy peasy. Okay, now what is not easy is the affective domain. So let me go over here. It's a little bit strange on this one. So the affective domain, let's think about it this way. If you make it just a square, let's say I just want to make a square. I don't want to have a rectangle at all. Well, if you have just a square, that would make y equal to 0. Now we know y can't actually, it could be 0, but y would be equal to 0. Let's put it that way. And that would make 4x equal to 24, because your 4x, let me put this way, all 24 of inches of your wire would be getting used to make your square, and you wouldn't have a rectangle. And that, I take it back, that is totally possible. You could make it so it's all square, no rectangle. That would make x equal to 6. So y equals 0 is as lowest you can get for y. Now what about if you got no square, if you just have a rectangle, right? No square. Well, if you have no square, that would mean that x is 0. Right? That's the lowest x you can have, right? None. So that's the lowest x. What would happen then? Well, then all 24 inches of your wire would be getting used for the rectangle. So 8y would be equal to 24, which makes y equal to 3. So my affective domain is 0, 3. I can actually have all of them too. So this is very much a hard bracket situation, because I can have 0, that would be no square, or excuse me, just a square, no rectangle. I could have 3, that would be just a rectangle, no square, right? Everything in between is also possible. All right, so now let's go back to step 6, which is we're going to find the first derivative and the first order critical value. Okay, well, the first derivative is easy to find. Just need a little bit of chain rule. So I guess I'll do this in green here. A prime of y would be equal to 2, 6 take away 2y to the 1 times negative 2 plus 6y. That would be equal to, distributed, negative 4 times 6 take away 2y plus 6y, and that would be equal to distributing that negative 24 plus 8y plus 6y, which would be 14y take away 24. All right, so that's the first derivative right there. Now, we don't have to worry about a critical value for the derivative not existing, because this is a line, so it doesn't have fractions, it doesn't have all that weird stuff. So there's the derivative. So the crit value, I don't know why I put that at an angle, but it'd be a prime of y, which is 14y take away 24 equals 0. So that would mean 14y equals 24, and that would mean y equals 24 over 14, which would be 12 over 7, because 2 goes into both of those. There's our critical value. Okay, now what do we do for step 7? Well, remember that we have a closed interval. So we're actually going to have to substitute all the values in. Sorry, that's my puppy playing with a toy. One second. And when we have endpoints that have hard brackets, we have to use the absolute maximum method. So we're going to use a method of calculus, and we're going to use the absolute maximum method. So method of calc to find maxmin. So let's see here. Maxmin. Okay, because we have these brackets over here, that's going to mean that we're going to use the absolute maxmin method, which actually I really like. It's just, you don't always get to use it. All right, so the absolute maxmin method says you're going to take your area function, and you're actually going to substitute in the endpoints and the critical value. So I'm going to put in 0, I'm going to put in 3, and I'm going to put in 12 sevenths. and I'm going to find the area. Simple as that. Using this area function that I had right here in step 4. Okay, so if I put 0 in, that'll be 36. If I put 3 in, I'm getting that by 0 going in would cancel this one out and would make this turn into 6. 6 squared is 36. If I put 3 in, that'll make this 0, and that'll be 3 times 3 squared, which would be 27. So 27. So this would be inches squared, because of course these are areas. Area is a two-dimensional thing, so it's going to have square units, as opposed to perimeter, which is linear, so it has single units, right? First degree units. All right, that leaves me the 12/7. The 12/7, I would just make a computer do it. So let me go grab Desmos real quick. I think I actually have Desmos up. Yeah, but I have it from another problem, but that's all right. I'll just type it in real quick. So we would have parentheses 6 take away 2 times 12 divided by 7, right? Close parentheses for the 12/7, close the parentheses to finish with that, and then square it, plus 3 times 12/7, close your parentheses and square it. And I get 15.428, or 429 if I round it. So that'd be 15.429 inches squared. So this is the maximum area. So the maximum area happens it's 36 inches squared at y equals 0. So if it's all square. So the maximum area, if all the wire is used, right? Think about what 0 meant. 0 meant you had y equals 0, which meant it was just a square. So if all the wire is used to make a square. All right, then the minimum area happens right here. The minimum area is 15.429, and that's if some of the wire is used to make, so let me put it this way, if the wire is used to make a combo of square and rectangle, that's actually the minimum. Which maybe there's a reason you want that, but and rectangle. So for whatever reason, maybe you want the minimum. And if you do, that's how to do it. Oh, sorry, I didn't go back to that. So there you go. So the maximum area is if all the wire is used to make a square. Again, that would be, right, y equals 0, all the wires used to make a square. The minimum area happens if you're making them in a combination. So the y is equal to 12/7. You could go and figure out what the x would be, etc., etc. They didn't actually ask for the dimensions. They actually just asked for the areas themselves. So the min area and the max area is all it was looking for. And then this one, where it's all used to make the rectangle, was kind of in the middle, so it didn't count as one of the answers we were looking for. Oh, and to get these values, remember, I'm substituting back in the original. I'm not putting them into the derivative. I'm putting them into the area function.